In this video, we're going to talk about how to set up an ICE table in order to solve for the extended reaction for an equilibrium limited reaction. Now, if you're not familiar with ICE tables, there's a link here to give you exposures to what I talk about in 151. Now, there's going to be a key difference between what we do here and what we do in 151. 151, my students are generally being exposed to limiting reagents for the first time, so I advocate that they build this table working purely in moles. 152, you should be familiar enough now with limiting reagents and working with reactions that you can work with this table both in terms of moles as well as molarity. So for equilibrium limited reactions, particularly ones where we're working in the gas phase or working with liquids, we'll actually use an extended reaction that represents the extended reaction in liquid in molarity, not actually in moles. But the rules are still going to basically be the same for this table. Now, whenever you're given these types of problems, you're going to find that you're given concentrations and the equilibrium constant. So in this case, KQ is going to be 9.45 times 10 to the negative 10. It's this equilibrium relation and it's these starting concentrations that are going to give us our extended reaction. So when you build your ICE table, I'm a huge advocate, make the left side reactants, make the right side products. You need to start with whatever information is given to you. So in this case, we have 1.00 molar H2SO3 reacts with 0.500 molar Na2SO3. What's the final H3O plus concentration? So our initial concentration for H2SO3 here is 1.00 molar. Our concentration of Na2SO4 is 0.500 molar. If you are not given a reagent or a concentration explicitly, assume that it's 0. So unless we were given a pH, assume then that we don't have any H plus in solution. And this could be true for any equilibrium reaction. If it's not specified to you, just treat it as 0. Now the change is what we're going to do differently than we did in 151, and the change is going to be represented now by the extended reaction. Now again, the extended reaction multiplied by the reaction coefficient is going to give you the mole change for that particular reactant. Now, I disagree with some professors in this regard when it comes to values of X. Some professors advocate that you should always set it up so your extended reaction is always positive. Well, I did my degree in chemical engineering, and chemical engineers basically let the signs kind of work themselves out in terms of X. So my convention is that it's always negative for reactants and always positive for products. And if you have a reaction that should be going backwards, meaning that you should lose reactants, you're going to get a negative value for your extended reaction. That's fine. I'm not bothered by that. Some professors are. So understand this video, I'm not setting my answers so this way X always ends up positive. Now, if we want to describe the change in H2SO3, all we have to do is take our extended reaction, X, and multiply by our reaction coefficient on H2SO4, which in this case is just 1. For H+, it's going to be X times, in this case, 2. So for every mole of H2SO3 that reacts, we produce 2 moles of H+. And our change in SO3 is going to be X times the coefficient, which again in this case is going to be 1. Our final table here needs to be the sum of these two cells. So in this case, my concentration of H2SO3 is 1.00 minus X. My concentration of H plus is 2X. And my concentration of H2SO3 is 0.500 plus X. These are the values I'm going to substitute into the equilibrium expression. So if you're still struggling with equilibrium expressions, you don't know how to write them, click on this video here. It'll actually give you little snippets on how to build up the equilibrium expression. In this case, looking at this reaction, KEQ is going to be the concentration of SO3 minus 2 times the concentration of H plus squared divided by the concentration of H2SO3. It's in these concentration blocks that we're going to substitute these values. So our concentration of SO3 in this case is 0.500 plus X. Our concentration of H plus is 2X, and our concentration of H2SO3 is going to be 1.00 minus X. We have a numerical value for KQ here, which is 9.45 times 10 to the negative 10. So we've got a value, we've got X. The next step is to solve, and I'm not going to cover this in this video. You're going to use something like Excel or you're going to use a numerical solver. But what you're going to get are multiple solutions to X. In fact, the highest power of X is going to tell you how many solutions you get. So in this case, we have 2X, which will give us 4X squared times 0.500 plus X. So if we distribute, we're going to get 4X cubed. That x cubed tells us we're going to have 3 solutions. So how do you pick one? Well, the big thing is we can't ever have a negative concentration. So our values of x, in this case, have to be greater than 0. When you solve this, generally what you end up seeing are at least one solution that's negative. Because our concentration of H plus has to be positive, whatever value we get for our extended reaction also has to be positive. The other limitation we have is that if our extended reaction is bigger than 1, meaning we get x is 1.01, our concentration of H2SO3 is going to be negative. So we're going to get 1 minus 1.01, which will give us negative 0.01. So use these in picking out which solution you're going to be working with. Sometimes you'll get multiple solutions. If you get 2 solutions, they're both equally valid, and then that's just what you get. There's 2 solutions to the equilibrium expression. The big thing here, though, is recognizing that in order to solve for this extended reaction, you had to build up your ice table, figure out how your final concentration relates both to your initial concentration and the extended reaction, and use your equilibrium expression in order to solve for that extended reaction.